Okay.
Without further ado, Trevor Hastie.
Well, good morning, everybody. It's a big pleasure to be here. This is a talk that normally takes an hour, but Sri told me to do it in half an hour, so I'm going to have to talk twice as fast, like a computer scientist instead of a statistician. Sri also asked me to talk about ensemble learners, which entails two of the tools that are included in the H2O suite. And these are very powerful tools that I'm very fond of myself, and so I'm going to tell you about them. So these are random forest and boosting. These aren't brand new ideas, but they're still very, very effective tools that I think everybody who does data science should be familiar with these, and it should be in their bag of tools. And they both build on trees, which go back a long way. So I'm going to tell you a little bit about trees first, and to do that, I'll start with a little toy example. Here we have a red class and a green class. You can see the red class is in the middle, the green class is on the outside. There's some overlap, and we want to build a classifier to classify red from green, just given the x1 and x2 coordinates. And shown in black is actually the ideal decision boundary. If we knew the population from which the data came, it's called the Bayes decision boundary. And so we can use this as a little toy example in 2 and higher dimensions. Here's the same problem, but there's no overlap, and sometimes you have classification problems of this kind too. The red's entirely contained inside the circle, the green's entirely outside, but you only get given a set of points and you have to estimate this decision boundary. So that's another version of the problem. So this is a classification tree for trying to solve that problem. And I think you're probably all familiar with these kinds of trees. What it does is it asks a series of questions. You'll come in with a pair of coordinates for x1 and x2, and it'll ask you a question. So is x2 less than 1.06? If yes, you go left. If no, you go right. If you go right, you'll ask some more questions. Eventually, you get down to a terminal node, and it'll say you're inside or outside, or you're red or green. Right? So it asks these questions. And this can be fairly effective for building a classifier. It decides which variables to ask the questions of. In this case, there are only 2, so it doesn't have too much choice. And it can build a fairly flexible decision boundary, which actually I'll show you in a moment. Here's the decision boundary for these data. This is the noiseless case. And you see it's made like a boxy decision boundary to approximate the circle. And that box would come from asking these coordinate questions. Are we left? Are we right? And so on. And at the end of the day, all the points that the tree classifies as red are inside the box, and all those outside are green. So it doesn't do a perfect job. It's kind of noisy. And this is only a 2-dimensional problem. It does pretty well. It gets makes 7% errors. But in fact, you could actually get 0% errors if you knew the truth, because there's no noise in this problem. But it seems like it's fairly promising. Okay. Now, if you take the same problem and turn it into a 10-dimensional problem, you imagine I can have a ball in 10 dimensions with the red inside and the green outside, then this tree would make 30% errors. So the problem gets harder as you go into higher dimensions. If you add some noise variables, it's going to even get worse. But still, the tree seems fairly flexible. It's kind of non-parametric. You can find automatic rules fairly easy. So here's some of the properties of trees. Trees are very good at handling very big data sets, and they can handle mixed predictors. That means you've got continuous variables and categorical variables. Trees handle them equally well. It can ignore redundant variables. If you have redundant variables that don't really have anything to say, the tree will never choose them as any of the split variables. Trees can handle missing data fairly elegantly, and small trees are easy to interpret. Like this tree is a relatively small tree. The data are rather vanilla in this case, but we could interpret this tree by seeing which splits it cut on and so on. On the other hand, large trees are hard to interpret. Often we need a very bushy tree before we get good performance, and those are really hard to interpret, right? Because there's so many variables involved in the split. But the most damning thing about trees is that the prediction performance is often poor. And it turns out that's largely because of high variance. So trees are, just don't give very good prediction performance for general problems. So the rest of the talk is about ways for leveraging trees to improve their performance. And there's two main ideas here. One is bagging and later random forest, which was due to Leo Breiman. And the idea there was that an individual tree is very noisy. It's subject to variance. So if you can find a way of averaging many different trees, you can bring down the variance through averaging. And so bagging and random forests are ways of doing that. Random forest is better than bagging, and so that's a very effective method. And then there's boosting, which also is a way of averaging trees, but it does it in a way that also learns from the errors of the previous trees, whereas random forest has just averaging sort of independent trees growing to the data. And this is I think this is an accurate statement of dominance. Boosting dominates random forest, which dominates bagging, and they all dominate a single tree. But boosting is considerable. It's slightly more work quite a bit more work to train and tune and fiddle with, whereas random forests are more or less out the box. Okay, so here's bagging. So there's lots of details. By the way, these little pictures here, you probably can't see them, but that's a picture of our book, and I'm referring to pages and sections of the book. And if you notice at the top, this indicates that this talk is actually a part of a course that Rob Tibshirani and I teach, and so I've taken the slides from the course. So if any of you were thinking of signing up for the course, you can ask for a discount because you've already seen this part of it. But good luck with that, because my wife is the course administrator. So how does bagging work? You want to get different trees so that you can average them. But the trees are trying to solve the same problem. So one way to make them different is to shake the data up a little bit. And a way to shake the data is to take a random sample of the training data and not use the same training data. So if you change the data, the tree that gets grown will be different. And if they're different enough, you can average these trees. And when you average things that are different, you usually bring the variance down. Okay? So Leo Breiman's idea was to do bootstrap sampling of the training data. That means you sample, if you've got n training points, sample n points with replacement from the training data. That'll give you a different sample. Some data points will appear more than once, some not at all, and so shakes the data up. Grow many trees to bootstrap samples, thousands of trees, and then average them, and then use that as your predictor. Now, you can average them in different ways. The way I prefer these days is each tree will actually, if you're doing a classification problem, will at any given terminal node, it'll give you an estimate of the probability of class 1, say, versus class 2. So each tree will give you an estimate of the probability at this particular point that you want to make the prediction. Well, you just average those probabilities, and you'll get a better probability, less variance. So this is just a cartoon, showing the first tree to the original data, and then trees growing to bootstrap samples. There's a few of them there, but as I say, you're going to do thousands. Well, that kind of cleans up on this little problem to a certain extent in the two-dimensional case. Notice that that boxy decision boundary has become much smoother now because it's averaged many little boxy decision boundaries, and it smoothed it and got rid of the variability. Okay, and of course the classification performance increases improves as well. So now we're down to 0.03 from 0.07, right? So it's halved the misclassification error. So this bootstrap sampling, turns out that wasn't enough. If you want to get the benefit of variance reduction by averaging let's just say variables, you'd like them to be uncorrelated. If they're completely uncorrelated, when you average them, the variance goes down as 1 over the number that you're averaging. But if they're correlated, that limits the amount by which you can reduce the variance. So the key here is to have these trees, in some sense, uncorrelated with each other. The more uncorrelated, the more you'll bring down the variance. So Leo Breiman had another great idea, which was a way of decorrelating these trees some more. And that was to introduce an additional randomness when you grow the tree. So when you grow the tree, each time you make a split, you would search over all the variables and look for the best variable and the best split point to make the split. So random forest does the following. It says, I'm going to limit you to only m variables out of the full p. So let's say p was 100 variables, and I'm going to limit you to 5 variables. So you pick at random 5 of the variables, and you search for the split point, the splitting variable amongst those 5. And each time you come to split at a new place, you do the same thing. Right? So there's this randomness in which variable you use for splitting. Well, that decorrelates the trees more, and it means you get much better reduction in variance by doing the averaging. Okay? This is a ROC curve drawn Hastie and Tibshirani style. Usually they go this way, right? Which shows random forest outperforms, in this case, a support vector machine, and in green, random forest in red, and it also outperforms a single tree in classifying some spam data. Let's see, I had another picture of random forest. Okay, well, that'll come in a bit. Okay. And random forests have some other nice features as well. For example, you get for free in growing this random forest what's called out-of-bag error rate, which is leave one out cross-validation. And you get it completely for free in the same, during the same process as growing the forest, you get this error rate for free. So it's basically a one pass through the data, growing these trees, and you're done. Okay, so it's really an out-of-the-box method. This is just a little picture showing how the correlation between trees goes down as the number of variables you pick it gets smaller each time you come to split. So if you randomly just pick one variable out of the pool, the correlation between the trees is the smallest, and then the more you pick, the higher it goes. So this is just showing how the correlation works. There's a chapter in our book that describes all of this in more detail. Okay. So that's random forests, and I'll show you some further pictures on random forests in a bit. And then finally, we're going to talk about boosting. So boosting is another way of averaging trees, but it's a little different. And this is the original description of AdaBoost, which was proposed by Freund and Shapiro back in the late 90s. And you see, it's an average of trees. The C's here are all trees, and we're going to sum them up, put coefficients in front of them, and that's going to give us our new tree. But boosting works slightly differently. Each time boosting will look at how well it's doing, and it'll try and reweight the data to give more weight to areas where it's not doing so well, and then grow a tree to sort of fix up the mistakes. So it's not growing independent and identically distributed trees. It's actually trying to go after the places where the current model is deficient. And boosting appears to do better than random forests and bagging. So here's some performance pictures on those nested sphere examples. And so what I'm showing you is, I'm showing you test error on the left, which you want to be small, right? And number of terms, which in this case is number of trees. And so we see bagging in red on the test data, drops down and then sort of levels off. And here's the performance of boosting, which does, in this case, quite a bit better. This is 20%, this is 10%. So this is the nested spheres in 10 dimensions, where a single tree got 30% errors. So bag-in gets 20%, boost-in gets 10% errors. Okay? So the AdaBoost came with a very detailed algorithm of how you reweight the data. So the idea is you're going to grow some trees, and then based on the performance of the model so far, you're going to reweight the observations. They give very specific recipes for how you do the reweighting, and then you grow a tree to the weighted data, and they also gave you a recipe for how to compute those weights alpha. So the details are all there. It's fairly intuitive, but we won't dwell on that now. Now, one of the remarkable things was that when you boost, with random forests you tend to grow quite bushy trees so that they don't have much bias, but they've got high variance, and then you get rid of the variance by averaging. But with boost-in, depending on the problem, you might actually grow very shallow trees. And in this case, for this problem, here we're using boost-in with stumps. So a stump is a tree with a single split. So that's about the simplest tree you can get, right? One split, two terminal nodes, it's called a stump. And here we see in the performance of boost-in with stumps on this nested spheres problem. And it does really well. This is AdaBoosted, it's down to 1%. So there's something really special going on with boost-in. Okay. Here's something else that's at first sort of shocked the community. What I'm showing you here is training error in green and test error in red. And training error, so what you see is that training error goes down. Now, at some point, the training error hits 0, right, and stays 0. But the test error continues going down. So that makes it clear that boost-in is not using training error as the basis for learning its trees. It must be using something else, because once training error is 0, there'd be nothing left to do, right? So that's kind of interesting. Here's another interesting plot, because the early boost-in people would say that boost-in never overfits. And it's not hard to make problems where boost-in does overfit. And here's an example. The training error keeps on going down, but at some point the test error starts increasing, which means you're overfitting. So turns out what boost-in is doing is building a rather special kind of model, and we call it Stagewise additive modeling. And, you know, so this is like a generic notation. You can think of each of these bees being a tree, which is a function of your variables x, and it's got some parameters, gamma, which would be the splitting variables and the values you split at, and perhaps the values in the terminal nodes. And then we're going to add these trees together and give them coefficients beta, okay? Sometimes these bees are called weak learners. They like primitive predictors, right? So when you think of it from this point of view, this is sort of similar to models we fit in statistics all the time. So for example, generalized additive models are special additive models where each function is a function of a single coordinate, whereas this here is a function of the whole vector x of predictors. And there's things called basis functions, for example, polynomial expansions, which is of this form, okay? And there's many others. But one big distinction is that we typically, when we have models of this kind in statistics, we might optimize all the parameters jointly. And you've got this big sea of parameters, and you try and optimize them jointly. Neural networks are like that too. We optimize all the parameters jointly. But the thing about boost-in is that we optimize the parameters in what's called a stage-wise fashion. So each time we're going to optimize the parameters of the next tree or whatever it is we're growing, but all the rest is held fixed. So it's called stage-wise fitting. And it kind of slows down the rate at which you overfit by not going back and adjusting what you did in the past. And that might sound like it's a handicap or it's a limitation, but it turns out that's a very reasonable way of regularizing the rate at which you overfit the data. So even though boosting was first proposed for the classification problem, it's actually pretty much, it's really easier to understand for a regression problem. And in that case, what it really amounts to is repeatedly fitting the residuals, right? So that's about as easy as it gets. So let's say we have a regression problem. We've got a continuous response. We start off with no terms in the model. Say our model is 0, and the residual is just the response vector y. And so now you just go in a loop, and at each stage you fit a regression tree to the response, giving you some little function g of x. And then maybe you shrink it down a little bit, and we'll talk about this shrinkage in a minute. And then you update your model by adding this term that you've just created to the model, and then updating your residuals, right? So each time you take in the residuals, you're going to grow a little tree to it to fix up what you're missing, and you add that to your function, subtract it from your residuals, and keep going. So constantly fit the residuals. And each time the thing you use to fit it is some primitive little tree. But it's trying to fix up the places in the feature space where you're doing badly, constantly fixing up the residuals. And AdaBoost was doing that in its own way for classification problems. Okay? And this shrinkage is actually important too. It slows down the rate of overfitting even more. So you grow a little tree to the residuals, but instead of just using that tree, you shrink it down towards 0 by some amount epsilon, and epsilon can be like 0.001, right? And so that updates the model only by a small amount. Now you grow a tree to the residuals again. So, but you might get a slightly different tree now. So it gives you an opportunity to get lots and lots of little different trees to fix up the residuals and not sort of use up all your data in big chunks, right? All your degrees of freedom. And this is a cartoon, but it shows that by slowing down, here's epsilon 0.01, it takes longer to overfit. This is meant to be test error. Okay, so this next part I'm just going to skim over. There's a section in our book which explains how AdaBoost was actually fitting, if you study it from the right point of view, well, right from a particular point of view, you can see that it's fitting an additive logistic regression model. So it's actually, AdaBoost is modeling the log odds of class 1 versus class -1 by a sum of trees. And it's using an unusual loss function, the exponential loss function, and as a basis for optimization, as opposed to 0-1 error, right? Misclassification error, which we saw got down to 0. This is more like a likelihood. And when you look at it from that point of view, there's a picture which you can compare different loss functions, and this compares, for example, this exponential loss, which is, I believe, this blue curve, to binomial log likelihood, which is the red or the green curve. And so that sort of puts in the same framework as logistic regression with binomial deviance as the loss function. Understanding boosting as minimizing the loss function in this kind of stagewise fashion, that sets the stage for creating a more general class of boosting algorithms. And that's what's actually represented in the functions GBM in R and in H2O. And so the general model is as follows. It's stagewise fitting. You've got a loss function. You've got a response. You've got your current model, which is fm-1, where you might have already m-1 terms. And now what you try and do at each stage is figure out what's the best little improvement to make to your current model. So in this case, we required to find a little function b, right, which is a function of the features and some parameters, and a coefficient in front of it, beta. But this is all we need to optimize. So we need to minimize with respect to beta and gamma to find this piece, okay? And then we'd update our function by adding that piece in, right? Or we might shrink it down before updating the function, okay? So that's stage-wise additive modeling. Each time, these might be fairly simple functions and fairly easy to update those. Gradient boosting uses small trees to represent these functions. And that's what happens in GBM. And gradient boosting was introduced by Friedman in 2001. And what it does is it works with a variety of different loss functions and includes classification, Cox model, Poisson regression, logistic regression, binomial, and so on. And what it does is it basically looks at this loss function and it evaluates the gradient of the loss function at the observations and approximates that gradient by a tree and uses that as the basis for this estimating this function. So there's details that you can read about in our book and elsewhere. The one thing I want to tell you is that tree size turns out to be an important parameter in the story. Okay, and I'll explain that in the next slide, I guess in a few slides. Here's boosting on the spam data. That's the green curve. This is test error, number of trees. Look, we're up to 2,500 trees. This is gradient boosting with 5-node trees, so that's 4 splits. This is random forest, does slightly worse, and this is bagging. Okay? The one nice thing about random forest is that it doesn't overfit. So you can't have too many trees in random forests. It just stabilizes, right? Because the trees are all identically distributed. So at some point, you don't get any benefit from averaging more, but you don't lose anything. Boosting, you can certainly overfit. You might even argue here we're starting to overfit. But there's more tinkering with boosting. Okay. Just some details on the spam. Both random forests and boosting give you something called a variable importance plot. And this is for the spam data again. There's 57 variables originally, and what it's doing is showing you how important each of the variables are. And some are very important, some less. And so that's kind of useful, and some variables are left out completely. Okay? Skip that. Tree size. This is actually showing on the spam data the performance of boosting with different numbers of splits, so deeper and deeper trees. And the remarkable thing here is that stumps actually does the best. There's 10-node trees, and there are 100-node trees. This was actually AdaBoost. And the way you understand that is, if you think about, for example, if you fit stumps, each tree only involves a single variable. So if you collect the whole ensemble of trees, you can collect all those trees that split on variable 1, x1, clump them together. All those on x2, clump them together. And what you'll see is that you've got an additive model, no interactions. Right? On the other hand, if you have 2 splits, each tree will involve at most 2 variables. So that second order, that'll give you at most second order interaction models. So the depth of the tree controls the interaction order of your model. Okay? So why did, I bet you all know this by now, but why did stumps do so well on the nested spheres problem? Well, the decision boundary for nest is the surface of a sphere. And that's just a simple additive quadratic equation describes the surface of a sphere. And stumps fits an additive model. And in fact, if you collect all those terms, they sure look like quadratic functions for each coordinate, right? So the last thing I'm going to talk about in my overtime is a concept called learning ensembles. So both random forests and boosting somehow or other build a collection of trees and then average them together or add them together with coefficients. Okay? So you can think of it as 2 phases. The one is building up the dictionary of trees using whichever mechanism you use, and then the other is adding them together. Now, random forest just gives the trees equal weight and adds them together with equal weight. And boosting sometimes does that too, or sometimes modifies the weight with which you add them together. But this suggests something that one can do to go beyond these methods, and that is to take the collection of trees that either of these methods gives you and try and combine them together in a slightly cleverer way as a post-processing step. Okay? And one way to do that is with the lasso. So the lasso is a way of it's basically designed for linear regression. And if you've got a bunch of variables and you want to shrink some of the coefficients to 0 and set some to 0, the lasso is a very popular method for doing that. And what you do is you have what's called an L1 penalty on the coefficients. So the idea here is you take your collection of trees from, let's say, boosting. Now, you can think of each tree as a transformation of the predictors. Because if you take your training observations, the x's, and pass each one down the tree, it's going to give you a number. So that gives you a single vector for the training observations. One tree does, is the evaluation of each of those training observations by that tree. If you've got 1,000 trees, you're going to have 1,000 vectors. So now you can think of those as variables in a linear regression model, and you want to see how to optimally weight them, and possibly leave a lot out. A lot of these trees are going to be very similar, and so you don't need to have a whole forest to do as well. So this is a really nice way of doing that, this post-processing using the lasso. And this is just a little figure. It's in our book, which shows how that you can benefit from that. And the one real advantage is you can often actually get better performance at either the random forest or the boosting model, slightly better. But the big advantage is that you can get rid of the vast majority of the trees. So if you're actually going to use this model as in production, you don't have to have a gazillion trees around. You can have a much smaller subset. Okay, so I'll just end with a slide which says there's nice software for fitting random forests and boosting, both in R and in H2O. H2O can handle very large data sets, and that scales very large. It's very, very well. So that's it. Thanks for your attention, and I'm happy to take questions. Feel free to ask questions if you want. Otherwise, I'll be hanging around afterwards. Yes?
Yeah, I have a question. In doing the analysis with the boosting algorithms, is it possible to back off of the residual analysis?
To back off of the what?
Off the residual analysis only to a certain extent, so you can do modifications, say, on the fly to really do the analysis of the problem. So let's say you've got trees that are stumps and they seem to be linearly correlated to each other, and they're fairly long. And you have a fairly long. Is it on? Okay, great. Okay. Sorry? Yeah, sure. Okay, so you've got this boosting algorithm. You have a set of trees that seem to be linearly correlated to each other, associated to the residuals. Has it been explored to back off the residual analysis in order to keep, let's say, the gross root of that tree, in order to just adjust the further analysis of the residuals so that you can get some efficiencies, say, in a real-time processing of ingress data? So,
it's a little hard for me to hear you because the mic's not working. So,
okay, great. Can you hear that okay?
yeah, that's better. Yeah.
Okay, great. Sorry about that.
So you're going to back off in some way? Huh?
Yeah, so you've done, let's say, the analysis on your data, your training set. And so you've got stumps that are somewhat linearly correlated to each other as they are doing analysis on the residuals. Has there been any exploration in being able to back off the residual analysis up to let's say, a certain point that is grossly similar between certain sets or certain applications of this model, where then you would be able to do the analysis only on the further residuals? The idea being that you could then get some efficiencies in post-analysis so that it's more efficient for real-time processing.
Yeah, these models are really very open to tinkering. I mean, there's lots of ways you can tinker with these models. So if I understand correctly, you want to sort of stop the boosting and then do something else to the residuals. I mean, one thing you can do, by the way, is you could first fit a traditional model to your data, say a linear model, to get some really strong effects, and then take the residuals from that model and now run boosting on that. But I'm not sure if that's getting close to what you're suggesting.
Well, I guess what my point is that I'm looking to see that if you have, let's say, a gross model and your analysis begins to vary from what your new input data is that you're actually applying the model to, that you would be able to adjust on the fly with it, so that you don't have to go back and start from a root analysis.
I see, yeah. Well,
but
that's
you could back it off to a certain portion and then only reanalyze your residuals to a certain extent to allow more efficient application and real-time processing.
No, absolutely, yeah. So that kind of adaptivity, depending on I mean, you might have special data problems where things are changing, there's drift, or it may be changing with time.
Exactly.
Absolutely. I mean, in principle, you could just carry on learning,
Right. It seems like
as the residuals
model,
change, yeah. It's inherently capable of adapting in that way, I think, yeah.
Great. Thank you very much.
In a lot of our commercial applications, we choose decision trees over other methods because of its explainability. The interpretability you mentioned.
Yes.
Can you just comment on what work, if any, has been done to make explainability for the forests, for the wide groups of trees?
Yeah, that's a little harder. Let's see. So this is one of the main interpretability tools, this variable importance. This tells you basically which variables are the most important. So I can't actually see here, but it looks like exclamation mark in spam is one of the biggest predictors of spam, right? And dollar sign is the next, right?
I was thinking more along the lines of when you have a specific prediction,
Yes.
being able to explain to a user why that prediction is good.
Why that prediction? Yes. Well, that's always hard because you've got a function of many variables here. So what you're actually trying to do is you're trying to explain the structure of a high-dimensional surface. And boosting a random forest can fit fairly complex surfaces. So there's things called partial dependence plots, which can sort of say to first order, how does the surface change with age, and how does it change with price, and things like that. So you can, and those are sort of the main effect terms. So you can, basically what you're doing is you processing the surface to try and summarize it in some crude way. But otherwise it's inherently hard to interpret. But deep trees are also hard to interpret, by the way. Complicated, yeah. Yeah.
And I was just wondering if you can further comment on the types of problems or boosted trees are most susceptible to overfitting weather, as opposed to the types of problems where they do all right.
That's a good question. What sort of problems will boosted trees tend to overfit more versus not? I think, the cases where they tend not to overfit are cases where you can do really well. So we'd say where the Bayes error rate is close to 0. So, so that's a case where the classes are potentially well separated as long as you can find the right classifier, and then the boosting tends not to overfit so much. But if you're in a fairly noisy situation where the best you can do is to get 20% errors, and no procedure could do better than that, so that's a more noisy situation, well, you in those cases, you're liable to overfit. Because if you train for longer and longer, the boosting algorithm will fit the noise and on the training error do much better than you're supposed to do. But it's still amazingly resilient to overfitting, but it certainly can. And it's not hard to construct examples like we did here where it does. Yeah. And so that when you train in boosting, you have to watch out for that. I mean, there's various tuning parameters. There's the number of trees. That's an important tuning parameter. There's the depth of the trees. That's a tuning parameter. And there's also the amount that you shrink. And those are all three important tuning parameters which you have to take care to, use something like cross-validation or left-out data set to make sure you tune those properly. Whereas random forest, basically only one tuning parameter, which is the number of, M we call it, the number of variables you randomly select for splitting at each step. And that's pretty much it.
Hi. So I unfortunately had to step out right when you talked about stumps, so maybe you answer this, but if you would. I've talked to a number of people who use GBM a number of ways. Most of them seem to think that deeper trees fit better. Your slides hinted that a large count of stumps seem to do better on the actual test data versus the train. You have any comments on like why this tension in the observations of practitioners versus what you're seeing?
Oh, that's a good point. Well, of course, we had a very fake example where the optimal solution actually required just an additive model, which is what stumps can deliver. So in a case like that, where you really want an additive model, so and if you go beyond stumps, it's just going to be fit in second-order interactions, say, if you use depth 2, which is not going to help much, and it's just going to add noise to the solution. But in real problems, I mean, of course, that's not necessarily the case. And in real problems, you might need fairly high-order interactions, to solve the problem.
Thank you.
But you don't know in advance, And but controlling the depth is another way of controlling the variance of your solution. Yeah.
What I hear is that for random forests, deeper trees can perform better, where boosting trees,
Correct.
you can do
Yeah.
better with shorter depths.
Yes.
Can you describe the insights? Why is the case?
Yes. So random forest has no way of what we call no way of doing bias reduction, because it fits its tree, and all the trees are in a sense IID, right? And so the only way it can benefit from fitting many trees is to reduce the variance of the fit by averaging, right? So that's why if you need a model that's got quite a bit of complexity, you jolly well better grow a very deep tree so that it can get at the complexity. Even though it'll get at it with very high variance, you're going to get rid of the variance by averaging. So on the other hand, boosting is also going after bias. It's by definition looking for areas where it hasn't done so well, and it's going to fix up there. So that's why you can have shallow trees with boosting, because it can wait for later trees to fix up places where it hasn't done so well. This has to be the last question, I'm told.
Sure. So in the boosting method, is there a framework for quantifying the uncertainty of the results based on the uncertainty of the inputs?
Yes, so uncertainty analysis.
Yeah.
So there's been some recent work in quantifying the variance and therefore getting confidence intervals for predictions from random forests, and still ongoing work on boosting. And that was something that was missing before. So it's easier with random forests, and I had a reference in the talk. On my webpage, there's a reference with a student in our department, Stefan Varga, had this very nice method for getting standard errors for random forest predictions with essentially no extra work. Yeah.
Thank you.
Okay, well, thank you very much.